Hey guys, today I'm going to be going over Unit 6, Lesson 2, all of the math problems from this lesson. So I just want to preface by saying that this is a more difficult lesson and the math concepts in it are harder, which is why I'm going to go through every single problem with you on this lesson so that you can write down with me, take notes, pause and play the video when you need to, all that good stuff. So before we get started, you do need a piece of paper and you need to follow along with me. And if you get overwhelmed, just keep taking notes, pause and play if you need to replay it, and then come to my classroom or your teacher's classroom whenever you need help. So just try your best and know that I'm going to be giving the answers in this lesson because I know that these questions are harder. Okay, so don't get overwhelmed. Like, give yourself some positive self-talk as we go through it and just know, like, I'm going to help you out throughout the whole thing. You are going to need a piece of paper. You're going to need a periodic table, which you can get from my resource folder. You're going to need your chemistry reference guide, which you also can get from my resource folder. So please pause it because you do need this and you need to go to table B-10 for this lesson. And then you can also pull up Unit 6 equations if you want to. I have a document that summarizes equations if you want to kind of follow along with that, but you don't necessarily need that because I'm going to go through it. And then you need your calculator. I use like a Desmos scientific calculator online. So let's go through the questions, starting with problem number 8. This is the first math problem. It says, what is the molarity of a 250 ml aqueous solution that contains 18.7 grams of AgNO3? Ag is silver and NO3 is nitrate. And so I know that that name is silver nitrate. So it says, what is the molarity? The formula for molarity, there's a formula, is you take the moles of the substance being dissolved and divide it by the volume or the liters of the solution. So here's our solution. That needs to go on bottom. And then this AgNO3 is going to go on top because that's what's being dissolved. So we need moles of AgNO3 on top. And we need liters of the solution. It says the aqueous solution. That means that it's water. When you see the word aqueous, think of like water. We need the liters of solution on bottom. Right now, they gave us the amount of AgNO3 in grams, and we need to convert that to moles. We can do that by, on the periodic table, pulling up the molar mass. And so I'm going to do this and explain how to do it, and then I'm going to show y'all how to do it in a shorter way, but I do want you to understand what I'm doing. So to get the molar mass, when you're converting from grams to moles, you need to pull up the molar mass to figure out how many grams are in a mole. So what you do is you go to your periodic table and you look up each of the elements in that chemical. So Ag, N, and O. So when you look here, I see Ag right here, number 47, and you got to zoom in a little bit. Its molar mass is 107.868. So I'm just going to write down like 107.9 to round that off. Okay. And then we also need the nitrogen, which is up here. To zoomed in a little bit. Nitrogen is about 14. I'm not going to write down everything there. So we'll say 14. And then oxygen is about 16 when you look at that 15.999. So we're looking at the numbers on the bottom. And we're going to just go over here and write that down. So 14 and 16. If you notice, there are 3 oxygens because it says AgNO3. So we need to do 16 times 3. And because I don't memorize stuff like this, I need to multiply that myself. That's going to be 48. And now we just need to add all of these together. So 107.9 plus 14 plus 48. And I am getting 169.9. This tells me how many grams are in 1 mole. Okay. Now, as a trick, I want you to know how to do it, but I also want you to know in the future what you can do, because there are so many steps to these problems, is just look up the molar mass online. Like, just type it in and say molar mass and look at that. It's going to tell you the molar mass. If you type in the chemical correctly, it will add it up for you. And so you can in the future, to save time, and what I'm going to do for this lesson is just pull up the molar mass. If you want to do it by hand, that's great though. Okay, so now we have the molar mass and we're going to convert to moles. So we're going to multiply and put what we want to get to on top. and what we want to cancel out on bottom. And now we need to put in the relationship. See how my grams are going to cancel out? You need your units to be canceled out if you want the grams to cancel out so that you're left with moles, because this is on top and that's on bottom. This is kind of on top here, right? They're kind of being divided by one another. And when you divide something by the same thing, like 5 divided by 5, it cancels out. So grams divided by grams are going to cancel out. Now we need to put in the relationship though. And if we read right here, we said that 1 mole was 169.9 grams. So I'm going to put the 1 with the mole because it says 1 mole. And I'm going to put the 169.9 with the grams. It goes on bottom because that's where the grams are. And so now all I'm doing is 18.7 times 1, which is just 18.7, divided by 169.9. So it's really 18.7 divided by 169.9. So see if you can calculate that yourself too. What I'm getting when I do that is 0.11 and then a lot of like other numbers, moles of AgNO3. So now I can put that on top. That is what's going to go on top right here, right? I also need liters of solution. So for my solution, I had 250.0 mils of it, and I need that to be in units of liters. This is a little bit easier. I need liters on top. I want to get to liters, and I need milliliters on bottom. And I need to ask myself, how many milliliters are in a liter, or how many liters are in a milliliter? We need the relationship. And you can Google this. If you say how many ml are in an L, a milli is 1,000th. So there are 1,000 milliliters for every 1 liter. So we're going to be doing 250 divided by 1,000, which is just 0.250. It's just shifting the decimal over liters. So now I'm going to underline, I have my moles and I have my liters. And so now I can plug that in up here, 0.11 divided by 0.250, 0.11 divided by 0.250, and I'm getting 0.440 capital M. That is my answer for problem number 8. Okay, if you have any questions, then come talk to me or join my classroom. Next one, this is problem number 9. For a particular lab experiment, you need 150 mils of a 2.5 molar solution of ammonium nitrate. How many grams of ammonium nitrate will you need for the solution? Okay, so they gave us the capital M. If you notice, they gave us that 2.50 already, right? They also gave us the volume. They gave us the 150 milliliters. We just need to convert that to liters. So the thing that they did not give us was the moles. And they said how many grams. So what we're going to do is we're going to solve for moles and then convert it over to grams. Okay, so we're going to plug in everything that we know into this equation. And I'm just going to rewrite it down here. We know that capital M equals moles of solute, or the thing being dissolved, and that is the NH4NO3 divided by liters of what is our solution? I think it's just water in this case. So liters of solution. Okay, and they told us that our M was 2.50. So I'm going to go ahead and plug that in for my M. That is my 2.50. Moles, I don't know. So that's kind of like my X divided by liters of solution. Well, I know that I have 150 milliliters. So I just need to convert that to liters by dividing by 1,000, because I know that there are 1,000 milliliters for every 1 liter. If you look it up online, 1,000 milliliters for every 1 liter. So 150 divided by 1,000 is just 0.150 liters. So that's what goes on bottom, liters like this. And now I need to solve for moles. Moles are like my X, okay, like in math. I need to get X by itself. That's how you determine X. Right now, X is being divided by 0.150, and I don't want that there. So to undo this, I'm going to multiply by 0.150 liters so that it cancels out. But what I do to that side, I also have to do to this side. So I need to also multiply the left-hand side by 0.150. So 2.5 times 0.150 on the left-hand side is 0.375, and that equals my moles. I just did that times that, okay? So that's my moles of NH4NO3. So I'm gonna rewrite that over here, that I have 0.375 moles of it, and they want me to convert that to grams. Well, we can do that using molar mass. So remember, I'm gonna put what I want to get to on top and what I want to cancel out on bottom. And now I need to put in the relationship. And you see how my moles are going to cancel out like that. So you can do this by adding up and looking up those substances on the periodic table. You look up N, you look up H, you add them all together. But I am just going to look it up online, NH4NO3 molar mass. And it'll add up for me, 80.043. I'll just say 80.0 to round it and be a little bit lazy. So 80.0 is how many grams are in 1 mole of it, okay? I need to put the grams, the 80, with the grams. So in this case, it's going to go on top because I'm trying to get to grams, and the 1 is going to go with the mole. So now I'm just doing 0.375 times 80 because the 80 is on top. And I am getting 30 grams. Let me double check that that was one of the answer options. Yes, the answer there is 30 grams of NH4NO3. All right, next problem. You have a stock solution, okay, of 2.5 liters of 6 molar magnesium sulfate. However, you need 225 mils of a 0.500 molar solution. How will you dilute the solution, and how much of the stock solution will you need? Okay, so for this one, we are going to use M1V1 equals M2V2. So we have basically we need to figure out what was our original stock solution. At the beginning, it says you have a stock solution. That's like your original when you see the word stock. So originally I have in this container here, it's a 2.5 liter container, and the fluid inside is 6 molar. That's how potent it is. The molarity tells you how strong it is or concentrated. And I only want 225 milliliters. And I only want the solution to have the potency of being 0.500 molar. So it's saying how much, basically we can take some of this liquid out. We can pour it into here and then dilute it with water. And it's asking how much should we pour out? How much of the stock solution? So how much? We are going to be solving for V1. How much of the original solution will you need? So that's going to be my X, okay? And then my M1 is going to be 6.00 molar, okay? You may be wondering, why is our V1 not 2.5 liters? Why don't we know that? Well, we know we're not going to use all of that whenever we're diluting it. We're going to use just a little bit of it. We're going to take some of it out. So we aren't going to use that whole 2.5 liters. So we really are solving for our V1. My M2 is 0.500 M, and my V2 is 225 milliliters. And now I can plug it into this equation. So 6.00 times X is equal to 0.500 times 225. So let's go ahead and multiply out the right-hand side, 0.5 times 225. The way that you solve for this at this point is up to you. There's a lot of different ways to do it. So 6.00x. We need to get x by itself, so we need to divide both sides by 6.00 because right now it's being multiplied by it. So divide both sides by 6.00. So 112.5 divided by 6 is 18.75. So X equals 18.75 mils. That is how much we're going to take out and put into this container. And then we'll top it off with water. And that will give us a new concentration of 0.500. I think the answer on yours, though, I think it rounded it differently, is 18.8. Is that right? Yeah, 18.8. So that's the answer for number 10. So yeah, let's look at the next one now. So now we're doing a little bit of a different formula. If I even just skip my eyes down here, this is what it's asking for. It's asking for molality. So before we read all of that stuff, I have the formula for molality right here. Molality is different than molarity. Molality is moles divided by kilograms rather than liters. So let's figure out what our solute is and our solvent is. Winter is coming. You want to make sure you have the right amount of antifreeze in your car. The best mixture of antifreeze is 50% antifreeze and 50% water. The cooling system in your car has a mixture of 6 liters of water with 6 liters of ethylene glycol, which is antifreeze. What is the molality of that solution? So typically the solute is the thing that's smaller, but we have like a 50-50 mixture. Normally it's like 60-40 and you know which one's smaller and which one's bigger. But if you have like a 50-50 situation, then the water is going to be the solvent. And so we need moles of antifreeze on top. Moles of antifreeze on top. That's our solute, the thing that's smaller or the thing being dissolved. And antifreeze is C2H6O2 apparently, divided by kilograms of our solvent, which is H2O. Okay, so we're kind of just transferring this to make it make more sense. So our solute is antifreeze, which is C2H6O2. So all we need to do now is find the moles and the kilograms so that we can divide the two by one another. So let's do the moles first. It says that we have 6.00 liters of the ethylene glycol, which is antifreeze. This is ethylene glycol. We need to get that to grams. So how do we go from a volume to a gram? Well, it said that the density here was 1.11 gram per cubic centimeter. A cubic centimeter is equal to 1 milliliter. This is something that's always true. If you go into nursing, you may know, like if you heard they need 12 cc's of this medication, like a cubic centimeter, that's 12 milliliters. So 1 centimeter cubed is 1 milliliter. And so let's convert this liter to milliliters. So we want milliliters on top and liters on bottom. We know that there are 1,000 milliliters for every 1 liter. And so 6 times 1,000 is going to be 6,000 milliliters. And then we can use density here to say, okay, the density is 1.1132 grams for every 1 milliliter, because a cubic centimeter is a milliliter, right? So 6,000 times, you can use density basically to convert between grams and milliliters. So 6,000 times 1.1132 is 6,679.2 grams. We need that to be in units of moles. And so now we're going to go to moles and we're going to say, okay, moles, we want that on top and we want grams on bottom. And now we're just going to look up the molar mass and we're not going to add it up. We're just going to have Google help us out there. So the molar mass of that is 62.07. So we're going to plug that in. The 62.07 is how many grams, 62.07 is how many grams are in 1 mole, right? So we need to put the 62 on bottom and then the 1 on top. Basically, the number 1 is always going to go with the moles. And so now we're dividing. We're doing 6,679 divided by 62, and I'm getting 107.6 moles. Okay, so that is what's going to go on top, 107.6. And now we need the kilograms of water on bottom. Does it give us the water there? Thankfully for water, if I remember correctly, yes. The density of water is 1. And so if you have 6.00 liters of water, then that would be 6.00 kilograms of water. It's the exact same. For water, the density is 1 to 1. So you go from liters to kilograms. So it's the same. So the kilograms of water is 6.00 because the density of it is 1 to 1. So if you have 6 liters, you're going to have 6 kilograms of it. That's the only true for water. So now we're doing 107.6 divided by 6 right here. 107.6 divided by 6. And when I do that, I get 17.9 as my answer. 17.9 lowercase m. So molality is moles divided by kilograms. They gave us a lot of conversion work to do. We had to go all the way from liters to moles for the top. And then the bottom was a little bit easier. It was just like a 1-to-1 thing. And so it kind of gave it to us already. And we just divided those two against one another. Okay, next question here. The best mixture of antifreeze they talked about earlier is 50-50. The cooling system in your car has a mixture of 6 and 6. The molality, okay, thankfully they gave us the molality already. So that the molality is 17.9 m. The chemical formula of ethylene glycol is this, and the density is this. At what temperature would this mixture freeze? So the equation we use is the freezing temperature, and this means that it's the temperature, there's a normal freezing point for water, right? But when you mix other things in with water, sometimes the freezing point changes. So this stands for the change in freezing point in freezing temperature. Delta means change. So change in freezing temperature is what that means. This is a certain constant found in a data table that we're going to look up. A constant means it's always the same. And M, they already gave to us, thank God. Okay, so we already have M. So we just need to solve for the change in temperature to figure out when the mixture would freeze. So we're going to go look up this stuff from table B10, and we're going to do it for the solvent. So in this situation here, it's 50-50. So we're going to assume that water is our solvent. So we need the KF for water, and then the normal freezing temperature for water. This is table B10. You're going to go find your chemical here. So here's water right here, and the KF is right here. So the KF for water is 1.86, and the normal freezing temperature of water is at 0 degrees. So I'm going to write that down. So this is 1.86. and this is 0 degrees Celsius. So water normally freezes at 0. We're going to see how much it changes. And so now we're going to plug in our numbers, negative, and then the KF is 1.86 times 17.9. Okay, so we're just doing 17.9 times, or I'm sorry, I mean, it doesn't matter the order, but 1.86 times 17.9, and then there's a negative sign there. So negative 33.3 is what I get when I round. This is how much the water changes. So normally the temperature is at 0 degrees, right? So we need to do 0 degrees and then minus that 33.3. And that's obviously negative. It's like 0 minus 33. It's going to be the same. So this is the new freezing point of water when you mix in antifreeze with it. Isn't that cool? So now you have to get down to negative 33 degrees in order for water to freeze if you mix antifreeze in with it. So that should be your answer for number 15. Only 2 more, okay? So number 16, let's see, let's kind of read what it's asking here. So it gives us some information. We've got carbon tetrachloride. It's dissolving in nitrobenzene. It was placed in the freezer, and the temperature is at 0 degrees in that freezer. The temperature, hold on, I'm kind of being messy here. The temperature is at 0 degrees. Did the solution freeze at that temperature? If so, at what temperature, or if not, like at what temperature? So we need to figure out the freezing point of this mixture so that we can figure out, okay, when it's at 0 degrees, is that enough for it to be frozen or not? So we're going to do the same formula here, except this time, like this is our normal formula, but this time they did not give us the molality. So we've got to actually calculate that to plug it in. We've got to find our KF and then our normal TF. So let's do the molality part first. So in this problem, what is our solute? Well, the solute is the thing that's smaller being dissolved. So this one's 94.4. This one's 250. So the 94.4 is smaller. So the CCl4 is going to be on top. Okay. And then the kilograms of solvent are going to be on bottom like this. Okay. This problem is the longest problem. So just keep up with me. This one's going to be the longer one. And then there are other ones after this. So we may need one extra slide here. I'll go ahead and put that in. Okay. So we need moles of CCl4 on top and kilograms on bottom. And that will give us the molality that we can plug in here. So right now, they gave us that it was 94.4 milliliters. They did not give us the moles, but it said that the density is 1.59 grams per centimeter cubed. So we can convert it over to grams because we know that the density is 1.59 grams for every 1 milliliter because a centimeter cubed is a milliliter. So let's convert it over to grams, 94.4 times 1.59, and I'm getting 150.1 as my answer here, and that's how many grams I have of CCl4. Now I can take that 150.1 grams and convert it over to moles using molar mass on the periodic table. So again, I'm just going to look up the molar mass of CCl4. We did this earlier. It's 100, let's say 154, or maybe we didn't, maybe I did it earlier, but the molar mass of it is 153.8. So I'm just going to write down 154. That's how many grams are in 1 mole of it. So it's going to go with the grams on the bottom. So we're doing 150.1 divided by 154. And I'm getting 0.97 moles. That is what's going to go on top for my molarity. So I'm going to write that down on the next slide, 0.97 moles of CCl4. So now what do we need? We need the kilograms that go on the C6H5 NO2. Okay. We need to convert that to kilograms. So let's look at the density of it here. The density of C6H5NO2 is 1.2 grams per cubic centimeter. Okay, so 1.2 grams for every 1 milliliter. So see how my milliliters cancel out? So we're doing 250 times 1.2, and I get 300 grams of C6H5NO2. I need that to be in units of kilograms, right? So we need to convert that 300 grams over to kilograms. We want kilograms on top and grams on bottom. We know that there are 1,000 grams for every 1 kilogram. Kilo means 1,000. It takes 1,000 grams to have 1 kilogram. You could also look that up online if you want to. So this is how many kilograms of my solvent that I have. Remember that molality is moles of the CCl4, the solute, divided by kilograms of C6H5NO2. So it's going to be 0.97 divided by 0.300, making sure that my units are all correct. And I get 3.23 repeating for my molality. That is my molality that I'm going to plug in right here. So 3.23. I need my KF, and we need the KF for the solvent. Our solvent is C6H5NO2. So let's go over to our reference guide and find it. Here it is right here, C6H5NO2. The KF is 6.85 when you look at this column, and the normal freezing temperature is 5.7. So I'm going to write that down, 6.85 and 5.7. Okay, so this is 6.85. So negative 6.85 times, because that's a negative sign right there too, 3.23. And I'm getting negative 22.1 degrees Celsius. So the normal freezing point is 5.7. I'm going to write this down over here. We're going to do even one more slide. Where am I? The normal freezing point, the normal freezing temp, didn't I say it was 5.7? Yes, it was 5.7. And our change in temp came out to be what? Negative 22.1. Negative 22.1. So normally it freezes here, but it's going to go down by this much. So 5.7 minus 22.1 is what? 5.7 minus 22.1 is negative 16.4. This is our new freezing point. Our new freezing point. Okay, so now let's read the problem. It says the temperature dropped to 0 degrees Celsius. Did the solution freeze? So the temp in the fridge is 0 degrees Celsius. So is it going to freeze? Well, our new freezing point is negative 16.4. It freezes only when it gets down to that temperature, right? So if the freezer is at 0 degrees Celsius, but it freezes at negative 16.4, the answer is no, it did not freeze. And its new freezing point is negative 16.4. So hopefully that kind of makes sense to y'all. I know that was a lot. This one was the most work. I'm sorry. That's why I'm working through these, is because I wouldn't be working through them if I expected you to try to do them on your own. If you are, that's awesome. Last one is a little bit quicker. Again, it's the antifreeze stuff. And look here, yay, they gave us the molality here, so we do not have to solve for it. It says, if the summer temperature rise in coolant reaches a temperature of 108 degrees C, will it boil? So when you're talking about boiling, you need to use the boiling equation right here. So we need the KB and the normal temperature, the boiling temperature for water. Because remember, when we have a 50-50 mixture, your solvent is going to be water. So let's go look up the KB of water. For KB, it's over here. So 0.51. And the normal TB is 100. So let's go pull that up. So 0.51 and then 100. Okay, so we're going to plug that in. Our KB is 0.51, and they gave us our M already. So 0.51 times 17.9. 0.51 times 17.9. This is equal to 9.129. So that is how much the boiling point changed. So normally the boiling point is 100 degrees C. When you mix something with the boiling point now, so this is a positive number. So we're going to do 100 plus 9.129 rather than minus. For boiling, you're going to add them. For freezing, you're going to subtract them. So the new boiling point is 109.129 degrees C. This is the new boiling point, boiling temperature. Okay. It says, if the summer temperature rises and the coolant reaches a temperature of 108, will it boil? Well, it now boils at 109, not 100. And so if it reaches 108, it's still not going to be boiling until it gets to 109. And so the answer is no, it will not be boiling. And the new boiling point is 109 if it asks for that. So that's the last question. I hope this kind of helps. Again, these equations are provided for you. You need also, the table B-10 right here when you take your quiz. If you have any questions at all, please go see your teacher and they'll be happy to help you from here.